Hello everyone. This is a continuation of our lecture on theory of vibration. As we discussed in the class, the concepts which you are going to learn are not really limited to any kind of structure. It can be a building, it can be a layer of soil, it can be earth dam, it can be pile foundation and so on. And we discussed that we can discretize a system or building in a mass, a spring and dashpot. And we are always interested in looking at response of that system to either external load which is applied on the mass and system itself, or during earthquake when the ground is shaking and our structures resting on top of it. And we will start our analysis or concept of theory of vibration from a single degree freedom system. And as I discussed in the class, we will start the simplest one, which is 1 degree of freedom, 1 mass, 1 spring and 1 damper. And we will take a case without a system without dampening and system with a dampening. And then today we are going to continue our discussion where we have force acting on it, and that is also actually periodic force. And there are many examples we can see in real life where we have to design structure for loads which are applied during construction vibration or by exerted by motors or machine. So, let us start our analysis from single degree freedom system, but system is a free vibration, but it has a dampening. So, on Tuesday, the class which we missed, and on Thursday we talked about single degree freedom system, and in this freedom system we are looking at it has a dampener also, but we are looking at a case where there is no force vibration. And in your notes you should have this equation which is a response, and this has a dampening effect, and then this is our not natural frequency but circular frequency which is damped. And you also have in your notes that omega d is equal to omega 0 and is a function of zeta. Now, I have asked you to give this given initial conditions where time t is equal to 0, displacement becomes u0 and velocity becomes u0 det. And if you input this information, then you can find the constant values which we need to find for the parameters. So, instead of writing down these terms, but we are trying to find out value of C1 and C2, I will assume that, and I expect that you will find these values of C1, C2, and I am going to write what these values should be. Okay. Let's see. So, you should be calculating and the value of C1, or let's start with C2. So, C2 constant would be a value of u0, which is initial displacement, and C1 is u0 dot plus zeta omega 0 u0 divided by wd. Okay. Now, we know the value of these two variables. So, we can write a total response which will be e to the power zeta omega 0 t, and inside now we have u0 dot plus zeta omega 0 u0 divided by omega d and sine of omega d t plus u0 cosine of omega d t. Okay. So, this is your total response, and when we know the values of the omega and omega d, we can plot this response. So, let us try to see what the response would look like, and I am plotting here time and I am plotting here displacement, right. So, if I plot the complete response, we have initial displacement of u0, and then the system start vibrating, and this amplitude will start decreasing with time, unlike the system without the dampening. And this is your initial velocity, which is u0 dot. And if I draw a line tangential to all these peaks here, okay. So, this is what is called log decrement, and this decrease is proportional to e to the power zeta omega 0 t. Okay? And as the function time increases, amplitude start decreasing. Now that makes sense, and we also know this is a period. Now this is a damped period, so this is t sub d, which is nothing but 2 pi omega d. Now what is the wonderful part of this result, what we get, that if we plot this value, we can estimate what is the value of zeta. And this is a very complicated property of a material, and let me give you an example how this kind of information can be obtained in the field. So I mentioned in the class I was involved in a project where we were building a fairly large structure resting on a series of pile foundation. So pile foundations are deep foundation, and we wanted to know the system dampening property. So what was done in the field, we had a more like pulley connected to that. We pushed the system or pulled the system by given displacement, and we let the system vibrate, and we had the sensor. So we were recording the time decrement response of a system, and from that we calculated what is this curve, and from that we could calculate what is the value of z. This was very useful, and this has been done on real project. In fact, some cases entire earth dams have been pulled and allowed to vibrate to calculate damping property of the material. Okay. Now this is the case where we have systems freely vibrating. Now I think we are going to move to a case where we are system, single degree freedom system still, but are now system going to have a force vibration, and there are many applications of those cases. So let's start with that. So we are looking as response of a single degree freedom system, but now it is applied subjected to harmonic motion or excitation. And in this case, let's assume that motion has a form of q0 sine omega bar t, which is omega bar is a frequency of the motion, and our system is single degree freedom system. So we can write equation of motion as m u double dot, and we are going to start with undamped system. So our equation of motion becomes sine omega bar t. Okay. Now when we have this kind of equation, differential equation, our solution we know has two parts. One is called complementary part, and other is called particular part. Now complementary part solution is when we take this equation of motion and we make right hand side as 0. Okay. And the particular part must satisfy the right hand side. So I'm going to just write that, satisfy the right hand side. Okay. So let's start with complementary solution first. So our complementary solution will be, let's say, C1 sine omega 0 t plus C2 cosine omega 0 t, and we need to find the values of C1 and C2 by initial condition, and for that we already have the solution. We just finished it in the class on Thursday. So now let's focus on particular solution. So let's say particular solution has a form of u0 capital sine omega bar t, okay, and that has the same form as right hand side. So if we take this and now calculate the velocity part of that, so we just differentiate that. So this will be omega bar u0 cosine omega bar t, and let's come up with acceleration. Then it will be minus omega bar square u0 sine omega bar t. Okay. So, I have displacement, I have velocity, and I have acceleration, and I am going to input these value in this equation. Okay. Let us call that equation 1. So, let us do that. So, we have acceleration, which will be minus m omega bar square u 0 sine omega bar t. So, that is first term, plus we have displacement, which is u 0 sine omega bar t times k, and then we have q 0 sine omega bar t. Okay. Now, in this equation you can see that omega bar sine omega bar t is common, and so we can write in simple form that our u 0, which is an amplitude, is equal to q 0 over k, okay, and divided by 1 minus omega bar square over omega 0 square. Okay. And this ratio of omega bar over omega 0 is a very important ratio, and we generally define it as a beta, and this is called tuning ratio. So, it is called tuning ratio. Okay. So, we can write in that u 0 is equal to q 0 over k 1 minus beta square. Right. Now, we know the value of u 0, and we can now write complete solution, which has both a complementary part and particular part. So, let us go to the next page. These are very simple. Once you get one or two times these solution, then you will have no problem. So, our complete solution will be total solution will have complementary part and it will have a particular part. So, we can write here C1 sine omega 0 t, C2 cosine omega 0 t, plus we have q 0 over k divided by 1 minus beta square sine omega bar t. Okay. Now, there are two unknowns here, C1 and C2, and as we did in the previous cases, we need to find the values of that from the initial condition. So, let us assume what are the initial conditions. So, initial conditions can be that when time t is equal to 0, then displacement is u 0 and velocity is u 0 dot. Okay. Now, if you input these values, and I am going to ask you to leave certain space, I am going to leave some space in my notes here, because I want you to find out these values rather than I calculate these values. So, I am assuming you are going to do that, and you will find that, and here are the results, that C2 is equal to u 0 and C1 is going to be a rather long form, which will be u 0 dot over omega 0 minus q 0 divided by k multiplied by beta over 1 minus beta square. Now, you can assume that, oh, this is already given in all the books, why do you need to really do in your own notes? It is very, very important that you come up with this solution, because once you do it, then for other kind of motions and other kind of vibration, you know what to do that. Okay. So, I need to see in each of your notes how did you get C2 and C1. Okay. Now, we can write the complete response of a system, okay, and that system response will be written as, and I am going to write the final form, which will be q 0 u is equal to q 0 divided by k 1 minus 1 over 1 beta square sine omega bar t plus should be minus beta sine omega 0 t. Okay. Now, this system this is one part of the system actually. Uh, this is a case when system is in equilibrium. So when system in equilibrium means that u0 is equal to u0 dot is equal to 0. So this is a displacement at that time. Now if you look at that in this equation, q0 over k is nothing but static deflection. And what does it mean really, static deflection? It means that if you have a spring and of certain stiffness k and you apply a force of q, it's going to be in that position. It will pull, and so this change in that, this is a change in the displacement, and that is under static condition. We didn't move any kind of really, this force is not dynamic. So q over k is a static deflection. Okay, and 1 over 1 minus beta square is called magnification factor. Okay, and this is very important, and I'll show you why this is important. And let me turn to the next page. And what I'm going to do in the next figure, which I'm going to plot here, is I'm going to plot a value of beta and on the horizontal scale, and I'm going to plot magnification factor, which is 1 minus 1 over 1 beta square. Okay, and let me just show you what the result will look like, and I think you can find that in appendix of your book, and I want to focus on what really these results really mean in a practical application. So here is the result from plotted when we plot beta on a horizontal axis and magnification factor on vertical axis. What is interesting, you start with when magnification factor is 1, means that dynamic deflections are same as static deflection, and as the beta increasing, and there are some ranges of beta where very large magnification takes place. And when beta is equal to 1, then what we call resonance occurs and magnification is infinite. And when beta start increasing beyond 1, we have decrease in magnification, and if in fact you can see that magnification even decreases less than 1 and system completely damps down. Now this is a very good stable system, but if we are in this case where you can have beta, and what does it really mean? It means that natural frequency is close to the forcing frequency, in that you can have large amplification and in fact you can have resonance. Now does it really happen in real structures and systems? Let me give you 2 examples. One was a very interesting project, was really first failure which happened. You can find a really nice YouTube video on that, and it's called Tacoma Narrow Bridge Collapse. This bridge failed in 1940 or so. This was very large cable stretch bridge, and many people believe that this failed due to resonance of the bridge vibration. I want you to watch this YouTube, and then I am also going to give you an example of what really can happen and kind of damages can happen due to resonance. So we have discussed about Mexico City earthquake which happened in 1985, and during this, in the city there were very large number of structures which was between 6 stories and to 12 stories. And what happened, the fundamental period of these buildings from 6 to 12 story were very close to the fundamental period of the motion by which they were subjected to. So most of the buildings which damaged during earthquake were 6 to 12 story, not shorter than that, and many tall buildings survived very well. This is another example of resonance. Okay, so this concept is not just hypothetical concept, we have to really pay attention to that, and we are going to really look at some example design problems where this becomes a very important issue. So I'm going to take a break, and then we are going to talk about damped force vibration. So we are going to now move to a system which has a mass, and it has a spring and as a dashpot, but now we are applying a motion which is a vibrative motion subjected to that, and that is still q0 sine omega bar t. So it's like a modified case of the previous case. Probably in the last section I skipped few steps, but I'm expecting that you will fill those one in, and I will go rather a little bit slowly in this section. Okay. So we can write our equation of motion as mass time acceleration, damping time velocity, stiffness time displacement is equal to q0 sine omega bar t. Okay. Now we can divide this equation by m, and so we are going to do couple of things. One is divide this equation divide by m, and then we are going to, we know that omega square 0 square is equal to k over m, and we also know that zeta is equal to c 2m over times omega 0. So I'm going to substitute these values in this equation, and if we can do that, you will write that equation turns out to be acceleration plus 2 zeta omega 0 velocity and omega 0 square displacement and q 0 over m sine omega bar t. So this is our equation of motion. Let's call it 1. Okay. Now this equation of motion, as you know, will have two parts. Solution will have two parts. One is complementary and other is particular, just like in previous case. So let's start with complementary solution. Okay. So we have complementary solution, but it will have a dampening effect included in that. So we can write u sub c t, I'm writing about complementary solution, is equal to e to the power zeta omega 0 t and then c1 sine omega d, which is a damped frequency, and c2 cosine omega d t. Right. Now this is a complementary, and we look at now our particular solution. So particular solution would be u sub p t is equal to c3 sine omega bar t plus c4 cosine omega bar t. Right. And we can find a corresponding velocities and acceleration for this. So we can write, and we can find velocity, and that will be omega bar c3 cos omega bar t, and this becomes omega bar c4 sine omega bar t, and we can find acceleration, and so we will have this one omega bar square minus c3 sine omega bar t minus omega bar square c4 cosine omega bar t. Now we can substitute the value of displacement, velocity and acceleration in equation 1, which I want you to do that because it is a rather long equation. So I'm going to skip a step, couple of lines where you will be inputting these values in equation 1. And what I am going to write after you rearrange all these terms, your equation can be written in sine omega bar t omega 0 square c3 minus omega bar square c3 minus 2 zeta omega 0 omega bar c4, and then you will have here cosine omega bar t multiplied by C4 omega 0 square minus C4 omega bar square plus C3 omega bar 2 zeta omega 0, and on the right hand side you will have Q0 divided by m sine omega bar t. Okay. All right. So, I am sure you will get this equation. Now, what we are going to look at the case. So, we are going to look at two cases. One, we are going to look at case where case number 1, where omega bar t is equal to 0 plus n pi, where n is a positive integer, And for that case, when n is a positive integer, we know that sine omega bar t will be always 0, and we will know that cosine omega bar t will be always 1. So, if we input these values in the equation which we had, this one, right. So, I am going to keep here that sine omega bar t will become 0 and cosine omega bar t becomes 1. Then what happens to the equation? This becomes 0 too, and this equation becomes C4 omega 0 square minus C4 omega bar square plus C3 omega bar 2 zeta omega 0 equal to 0. Let us call that equation 2. Okay. And now we are going to look at second case, where we have the omega bar t is equal to pi by 2 plus n pi, and for that case we know that cosine omega bar t will be 0 and sine omega bar t will be 1. And if we consider these conditions and in the previous equation substitute these values, we will have the following equation, which will be omega 0 square C3 minus omega bar square C3 minus 2 zeta omega 0 omega bar C4 is equal to Q0 over m, and let us call this equation 3. Now, if you look at equations 2 and 3 carefully, only unknowns in these equations are C3 and C4. So, you have two equations, you have two unknowns, and you can find these values. And you will find that C3 is equal to Q0 over k times 1 minus beta square divided by 1 minus beta square whole square plus 2 zeta beta square. Okay. That is the value of coefficient C3, and coefficient C4 is Q0 divided by k, and here is minus 2 zeta beta 1 minus beta square plus 2 zeta beta square. Okay. So, these are value of coefficient C3 and C4. Now, we can write the general equation. And so, general equation of motion for the force 1 degree system would be u displacement e to the power minus zeta omega 0 t plus C1 sine omega d t plus C2 cosine omega d t. Okay. So, that is your complementary solution, and that solution giving this solution will give you displacement which are going to decay with time, and eventually the contribution of this part becomes negligible. And then you have a part which is a particular, and that will be Q0 over k, it is common out, and then one other terms which are common is 1 minus beta square whole square plus 2 zeta beta square, so that's also common, and inside this bracket is 1 minus beta square sine omega bar t minus 2 zeta beta cosine omega bar t. Okay. So, you can say, well, we still have two unknowns. We have unknown of C1 and C2, and where would we get these values? Well, that come from again initial conditions. So, we have to come up with initial condition, and for these initial condition we will find values of C1 and C2. Now, we will take an example problem, then we can see how it is really done. So, it is important to know, if I just plot a typical response of this system, which is subjected to the force vibration, which has a particular solution and a complementary solution. So, let us look at what would it look like. And so, the solution would look something like that. Okay? And I want you to just look at the graph rather than values. So, what we have here, total solution displacement is this shape, okay, and it is decreasing, but very small amount, and the contribution from that complementary part comes that, and as the time goes its contribution completely diminishes, and then we have a steady state part which remains constant over a long period of time, is slowly decaying it, decreasing it, but you don't really see the effect in a short number of cycles. Okay. Now, there are lots of other very important information which comes with these kind of solutions. So, let us take an example problem, and in the class on Tuesday I am going to talk about different applications of these equations of motions, and we will be solving numerical problems both as assignment, and I am going to start and give you idea how do we start those kind of questions. So, I am taking an example which is in the textbook and just starting some points in that. So, we have a system, okay, and it has one mass, and let us assume, and this mass or weight of is 1000 pounds, and it has one spring, and stiffness of a spring is always given in pound per inch, or just be careful of the units, and it has one damper, and dampening C coefficient is given always in pound second inch. Okay. And this system is subjected to a force and that is Q sub T is equal to 100, and that is pound sine pi t. Now, you can say, well, what is this system like? Is this real system? Yeah, this is a very real system. I want you to think this system to be like this. We have a mass, and we have a spring connected to that, and a dashpot, and we are subjecting this mass to a force which is Qt. Okay. Now, what does this represent? It can represent a foundation, this can represent the soil, and stiffener represents the stiffness of soil, damper represents the dampening property of the soil, and this may be represented by a motor which is resting on this foundation, and we are interested in calculating what will be the maximum displacement this foundation will be subjected to, because we have to design that. Okay. So, these are not hypothetical problem, these are really design problem. Okay. So, let's proceed with this one. How do we do that? We need to calculate complete response of a system. So, let me see if I can magnify this a little bit. No, that's not. Okay, let's stay with this one. Okay. So we need to calculate in this system, because if we write our previous equation, and which is written right here, this is a equation of displacement of a system, and but in this one, to calculate the response, I need the value of C1 and C2, right? And I need to start with initial conditions, so I can calculate the values of C1 and C2. So let's assume that initial condition, the one is when t is equal to 0, our displacement is 0 and our velocity is 0. So I'm going to start with that. Okay. So we will input the first condition, which is displacement is 0. So our complete solution, this is going to be e to the power zeta, and please write down omega, and 0 becomes 0, and then C1 sine omega d time is 0 plus C2 cosine omega d time is 0, okay, and plus we have, I hope you can read it, let's see, okay, and then we have q0 over k 1 minus beta square plus 2 zeta beta. There is no term of time here, so it does not get affected, bracket 1 minus beta square, and now we have sine omega bar t is 0 minus 2 zeta beta cosine omega bar t 0. Okay. So now if we look at this equation, that when sine is, this is 0, then this term is 0, this term is 0, this term becomes 1, and this term becomes 1, right. So we know that that happens. So let's see what comes out to be when we input this value. So we will have and this becomes 1, right. So we will have, from this section we will have C2 plus, and actually there is a minus sign here, so it will be minus q0 over k times all of this term 1 minus beta square whole square plus 2 zeta beta square, and then we have in the denominator 2 zeta beta, which is coming from here. Okay, got a little rather messy, but this is the value and this is equal to 0. So we can write that our coefficient constant C2 is equal to q0 over k divided multiplied by 2 zeta beta 1 minus beta square whole square plus 2 zeta beta whole square. Okay. So this is coefficient or value, you can say parameter C2. Okay. By assuming that our displacement is 0 when time is t0. Now to calculate the other coefficient, which is C1, we need to think about our velocity. Okay. So when time t is equal to 0, our velocity is 0. Okay. Now first of all, we have to take this our complete solution, okay, which was in your notes. Let me just refer to that equation. Okay. So this is your complete solution. Now first of all, you have to differentiate it to calculate velocity. Okay, and I hope you all of you remember how to differentiate that, and I need to see that those one in your notes. So I'm going to skip some terms here. Okay, and I need you to differentiate that. Okay, and after you differentiate it, you will be calculating value of C1. So I'm going to skip some page here space, and I'm going to write the value of C1 you should be getting, which will be q0 over k omega over omega d times beta square minus 1 minus beta square over multiply square 2 zeta beta square. Okay, that is the value of constant C1, and you should get this value. Now, after we have the values on C1, C2, we have both complementary and particular solution. We have values of everything, and we are ready to plot displacement with time for the system. Okay? And before you start plotting that, we need to calculate some basic properties, such as omega 0, which is under root of k over m. And here I want to caution you that be careful with the unit system. Now we know the weight is equal to mass time g, and we are given the weight of that is 1000 pound, right? So we can write either this equation as root of k weight, and we know g in 32.2 feet per second square. It will be consistent with units, so we can write here, and we are given stiffness in pound per inch, so we need to convert that. So we have 100 and times 12 times 32.2 and divided by weight is 1000, and we will get frequency at 6.22 radians per second. So this is a natural frequency in radians per second of this system. We also can calculate zeta, which is cohesion divided by 2 m omega 0. Again, m is in mass, so we need to convert into weight. So we can do c times g times 2 w omega 0. We can input the value of cohesion. We know the weight, we know g, we know omega 0. So we will get this value as 0.093. And this value is much smaller than 1. So this is a underdamped system. And we also can calculate omega d, which will be omega 0 under root 1 minus zeta square. We know the value of zeta, and this comes out to be 6.19 radians per second. So you can see there is not much difference between damped frequency and undamped frequency. We also need to calculate value of beta, which is omega bar over omega 0, and that will be pi radian per second divided by 6.22 radians per second, and so this comes out to be 0.505. Now you know beta, omega d, zeta, omega 0. We already know the value of q, which is 100 pound, and we know omega bar. So we can substitute these values in those equations, and you will get the response something like this. Okay, right? We can get the response which will have decay with time, and you will have a steady state response. Now I think I'm going to stop here, and we will discuss in the class how do we really use this kind of information in our real design. And so far we have talked about harmonic motion. We can also think about these motion not being harmonic but a pulse motion or impulse motion, but I'll discuss those in class on Tuesday.